that is available for the exam. One is how Maxwell's equations lead to an electromagnetic wave. And so you have two things really that could be done with this. One would be to go through the derivation of how the Maxwell's equations lead to a wave equation. And that's a rather complex derivation. So it's a low probability, but it's one of the things we can have. And so here I have the steps for that derivation, and then actually showing the work in the little box. Obviously, I copied that box. I didn't make that box myself. Don't remember the source of it. And so that derives to get to this wave equation. Now, that wave equation in one dimension is derivative, second derivative of a function with respect to time squared is equal to, and I gotta come over here and make sure, speed of the wave squared times the second derivative of the function with respect to position squared. So this here is a wave equation. You have a function, notice those are partial derivatives. Partial derivatives means if you're doing df dt, x is just a constant. You don't worry about any chain rule things. You don't worry about any product. You just have x is a constant. And likewise, for the df dx, then t is a constant. And so if this is true, then f, and I'll put it, f, which is a function of x and t, can describe a wave. So the more likely thing that I would do if I was going to do something with Maxwell's equations is actually give you a function and say show or determine if this is a solution to the wave equation. So you would just test the function. So let's take a potential function. And see if that's a solution. Now that doesn't look like a good solution, but see if it is a solution. And so how would I test to see if this green function is a solution to that wave equation? That's exactly it. So actually, getting my sizes confused. So d f dt is equal to, well, let's rewrite this. It's easier to do the derivatives if you write it that way, because if I do it with respect to time, the e to the ax is a constant. So that's what I get for the second derivative with respect to time. Not doing it in such gross detail. Doing the second derivative with respect to position gives me and so to check those, I would simply put them in and say is well, let's put it in the same order. Is that true? Now, we'll notice right away that we can factor out all the stuff that's x and t. That is, I have so I have these on both sides. So those are always equal. I can cancel the a's. And this is true if b squared equals c squared. And so it's a solution with the speed of b. So I come back here and say, aha, if it's x plus vt, that is b of the speed, then it's a solution. And in fact, any function of x plus vt is going to be a solution. Even though, what would this function look like? As let's say, as time progresses, you stay in one location, what would you see? Just get larger and larger and larger. Unless a is a negative value, because there was no restriction on a. If a is a negative value, then it gets smaller, smaller, smaller. It would only be physical if a is a negative value, and what this would actually be is your wave just spreads out. Okay, so that's what you could do with that. Derivation, long, difficult, unlikely, or doing the testing, which requires you to do the derivatives. Okay, then we had the brachistochrome problem. This was a problem in minimizing the time for light to go from point A to point B. So once again, here I have, this is a much shorter derivation than what I did in class. What I did in class, I did a whole lot of explaining, and I did a lot of calculations. This is going to the shortest way possible to do the brachistochrome problem. So the shortest way possible.
Wait, you want us to do the longest?
No.
Oh, okay.
No, just do it right. Okay. I did it the longest. In the end, it's the same work. It's just this here went straight to the forms that quickly convert, instead of the ones that you see as you go through. So the first thing you had to do there was find an equation for the path length in material 1 and the path length in material 2. And then the time is equal to the sum of those path lengths divided by speeds in each medium. And so that's the first equation that's shown here. That's path 1, L1, and this is L2. Pythagorean theorem. So this here defined A as the distance from the interface to point A, B is the distance from the interface to point B, and the direction is normal to the interface. And then X is the distance from where the light goes through from one interface to the other to where A is parallel to the interface. And D is the separation between A and B in the direction parallel to the interface. And so using those, just use the Pythagorean theorem that this here. So that's A, that's X, square root of X squared plus A squared is the hypotenuse. This other one, this is D minus X. So B squared, whoops, put square because I said it, B squared plus parentheses D minus X squared, square root is the hypotenuse. And then took the derivative with respect to time, and this is where it was done quickly. When I did it, my derivative with respect to time had many more steps in it because I said, well, okay, so I'm going to have 1 over square root times the chain rule, and so I have the 2x on top, and the 2's cancel, 2 with the 1/2. And here I just have straight to the answer. And then recognizing that this right here is the definition of sine of theta 1, if this is theta 1, because this would be the hypotenuse, and the opposite side is x. And likewise, this here is the definition of sine theta 2, because once again, the hypotenuse is on the bottom, and d minus x is the opposite side. And so just replace those. And for minimizing we took the derivative and set to 0, so set that to 0, and out pops Snell's law. So it's the same basic work, it's just I did a lot of explanation showing steps in the middle that aren't shown here.
So, do we do any calculus on these things?
The calculus is right here. Yeah. Yeah, you first make the equation for the time it's going to take to go from point A to point B, and then to minimize, you take the derivative with respect to the variable that you're minimizing with respect to, and set that derivative equal to 0. Well, I just explained all the way through. The last thing is talking about the Fraunhofer diffraction. So we had two outcomes for Fraunhofer diffraction. You are not going to have to go through and do the derivation of either of these. You should understand, the method of this integration, but I'm not going to have you do it because it's something that you wouldn't get it right. There's no point in asking you questions that I know you're not going to get it right. Excuse me? Okay, so what could you do with this? Well, you could be asked to find the locations of the maxima or the minima for these two outcome equations. So you could be given this equation or this equation and asked to find, for instance, where are the maxima, where are the minima. So how do you find where the maxima and minima are? Yeah, derivative again. Now, with the one on the left, it's really pretty simple. Let's just do this for each one. Derivative cosine is 2 sine, right? Well, minus 2 sine. And then chain rule. Derivative of sine is cosine. And so that's the equation for the derivative. I think I did that right. And so what do I do with that derivative? Set it equal to 0 and find the values of theta that will make that equal to 0. Well, the first thing you see is, well, if cosine theta is 0, not pi equals theta equals, man, I just rebooted this because it wasn't working right. It appears that it's still not working right. So for cosine theta to be 0, we need theta is equal to 0. And we can only go from pi over 2 to minus pi over 2. So theta equals 0 is the only option in that range. Or we're going to have this thing here equals 0. Or, oh wait, yeah, no, the cosine I was wrong. You were right. Equals 0 or pi or etc. So equals some integer times pi. Excuse me. So we have a whole lot of situations here that are going to equal 0. What was that? Well, yes, if you shine no light. We're assuming you're shining light. Yeah. And so we now, I forgot there's one more term. I did do my derivative right. I forgot one more term. It's 2 cosine n time. Yeah. I forgot to write that. We take the derivative of cosine squared. That's 2 cosine theta d cosine theta. The d cosine theta I did. And bring down the 2 I did, but I forgot that term. So that gives us a third option. Well, this one here, that one's useless. Of course, we know that at plus or minus 9 degrees, we're going to have them. So this one here is going to be one set of solutions. That gives us the simple relation that d sine theta is equal to m lambda. So that's one set of solutions. And if we go back, we can say right away, well, if theta is 0, then we're going to have cosine is 1. So those are solutions for maxima. Which means that these other set of solutions must be the minima. And these are pi d sine theta over lambda is equal to, and cosine is 0 at pi over 2, like you said. So it's m plus 1/2 times pi. So that's pi over 2, 3 pi over 2, 5 pi over 2, and the negatives there. And so once again, quick math gives us d sine theta is equal to m plus 1/2 lambda. And that's our solution for minimum. What was that?
What was the second term that you had equal to? The first one is d sine theta.
The first one was d sine theta is equal to m lambda. And I just went and checked with my original equation. Since that would give me sine theta is equal to 0 was one of my options, I just went back and said, what if sine theta is 0? Then I have cosine squared of 0, which is 1. That's got to be a maximum. So that's why I said, oh, that's got to be maximum. I could have done the second derivative test, but I figured I'd just do that instead. Because my maxima are going to be non-zero, my minima are going to be 0. So this one here, if I would have put this in, I would have had, the where did I write that? M plus 1/2 pi is what I would have for the pi d sine theta, and that's cosine 0 out. That would give us zeros for minimum. So those are the equations for maxima and minima. This is found very strictly, whereas what we did in class was found in a little more hand-waving, although a very valid way. So that's how we would do it for the double slit. And you can do the same thing for the single slit. Now, the single slit is a little more involved for the derivative, but you're going to have the same method. You're going to have bring down the 2, have this whole thing repeated, and then the derivative of the thing inside. And so it's going to give you, once again, 2 conditions, one that's maxima, one that's minima. That's it for what could be on the exam based on calculus. So any questions before I move on to new material?
Oh, we're doing that?
Yeah, we're doing that. The new material is relativity, yeah.
But I didn't write the last score. Yeah, there.
And I mean, you can always look at it on Windows.
I like my paper.
Okay. Okay, now, as you can see from my scribble outs, we're going to look at Lorentz transformations in 4 vectors. So we're going to be looking at some new words. Lorentz, that's the dude's name. I don't remember his first name. He's really important. I should. 4 vectors are things that we can define that have a magnitude that is invariant under transformation. Got it? Very clear, yeah. go right and move on with it. What this means is, if we take, well, for a three-dimensional vector, it's simple. The magnitude of the vector is x squared plus y squared plus z squared, right? So if we take a normal 3D vector, we find its magnitude. If we change from one reference frame to another reference frame, it is not going to be the same. No. If I have a meter stick like this, and it's traveling like this, in my reference frame, the length of the meter stick is 1 meter. But in your reference frame, assuming I travel at relativistic speed, of course, what's happened to the length of the meter stick? It's shorter. So it's not going to be the same. Now, if I put it at a different angle, I would have the length parallel to the motion short of the length perpendicular is the same. So if you were watching me travel and I twirl the meter stick like this, you'd see the meter stick getting longer and shorter. Bizarre, right? But what we're looking for is something that's invariant, something that doesn't change into your reference frame. Something that, for instance, if I'm twirling it, of course, it's not going to be a stick because that could be it. You wouldn't see any changes with it. So what we come up with for doing this is using light. If we have light, we know that light always travels at the same speed, regardless of the reference frame, as long as we're back. And we know time is going to go at a different rate in a different reference frame, and we know length is going to be contracted in a different reference frame. But we should be able to make an equation that's invariant for this. So what we do is we say, let's suppose at time equals 0, I have two reference frames, one that we label without a prime, one that we label with a prime. And at time 0, they're crossing, so they both agree where the origin is. So they both say, oh, at time 0, x is here, x is 0, y is 0, z is 0. And there's a light at the origin that flashes at time 0. So do you understand the problem or the simulation? So in my reference frame, when this light flashes, how does the light go out? What shape does the light make as it goes out? It makes a sphere. So in my reference frame, I'm going to have a sphere that has a radius equal to ct, right? Now, if I'm flying by and I see this light and it's expanding out in a sphere, and you look and you see that light, what shape does the light going to make as it expands out in your reference frame? Still a sphere. Doesn't seem right. Doesn't seem right because if I take a meter stick and I say, in my reference frame it's 1 meter this direction, 1 meter this direction, you say, well, his meter stick is not 1 meter in this direction, it's only 1 meter in that direction. But with the light, there's something else going on, and the difference is simultaneity. You would say that I did not measure one side and the other side at the same time. It's really a sphere, but it looks different in the measurement because I measured this side first and that side second. So it's going to be a sphere in both reference frames with the radius equal to speed of light multiplied by the time that has passed in that reference frame. Now, geometrically, we can also find in terms of x, y, and z what the radius is. What's the equation for the radius of a sphere? What? Okay, that is correct. That is correct. In terms of x, y, and z, for any point on the surface of the sphere. If the origin is 0. The Pythagorean theorem. This is a three-dimensional Pythagorean theorem, right? Pythagorean theorem is technically, I think, only two-dimensional, but it's the three-dimensional equivalent. The radius is x squared plus y squared plus z squared, all square rooted. So this gives us a relationship between time and position, and we can make a very easy 4-dimension invariant. That is, if we define my invariant as CT minus x, well, CT squared minus x squared minus y squared minus z squared, that's r squared minus r squared, right? What's r squared minus r squared? Trivial question. What's the answer? 0. And likewise for this one, CT prime squared minus x prime squared minus y prime squared minus z prime squared is also equal to 0. So there's a 4-vector invariant. So this is the space-time that we live in. Physicists say we live in a 4-dimensional space-time with 3 spatial dimensions, x, y, and z. And the 4th dimension is the speed of light multiplied by time. Now we have to come up with a way to find our invariance, that is to define the length of the vector. And there's a couple of different ways of defining the length of the vector. I'm not going to do too much vector math here because I'll just lose you probably in going through it. But what we do to define the 4 vector in the magnitude of the 4 vector is to take, we define x0 is equal to CT, x1 is equal to x, x2 is equal to y, and x3 is equal to z. So that means that I can define anything in terms of x0, comma x1, comma x2, comma x3. That's a 4 vector. And we say the magnitude of this is equal to x0 squared minus x1 squared minus x2 squared minus x3 squared. Now, like I said, there's a lot of linear algebra stuff I can show you that relates to this, but I don't want to confuse things too much. I am going to jump into linear algebra here in just a second. But that gives us our 4-vector invariant. Now, something that's important about this is it's something that doesn't change in one reference frame to another reference frame. So if you say, now this would be 0, it's kind of trivial. Another 4-vector invariant is the energy momentum 4-vector. That one's not equal to 0. But you can define the invariant and say it has this value, and it doesn't matter what reference frame you're in, that value is going to be the same. That's the key to these 4 variants that makes them useful, or these invariants that makes them useful. Now that we have that, which means that I've gone through about 7 slides here, there is the way of showing what I just did, how we find the magnitude. Notice it's called the dot product. But the dot product looks kind of funny. And it's because, well, we had to deal with there being the minus sign, one radius squared minus the other. Well, let's see what's good about this. Transformations. Based on this, we've learned that the time between 2 events in one inertial reference frame is linearly dependent on the time between 2 events in another reference frame. That is, we had delta t prime is equal to delta t times lambda. That's funny with the multiplication sign. Or times gamma. Time dilation equation. And we had length is also linearly proportional between the reference frames. Now, the proportionalities are times gamma divided by gamma, but they're linear. So that means that it should be not surprising at all that I should be able to write, or I should expect that I can write my time in one reference frame as a function of the time and position in another reference frame. And the position in one reference frame is a function of the time and position in another reference frame. Which linear algebra-wise, this equation right here, the set of 2 equations is equivalent to this one linear algebra equation. just like what we were doing when we were dealing with solving many variables, like in circuits problems, we can take this equation, the way it reads is this value is equal to this times this plus this times this. And so if you do that, t prime equals a times t plus b times x, you have the top equation. And then for the second time through, you go down one, this value is equal to this times this plus this times this. So x prime is equal to ct plus dx. So we're going to try to find this matrix, the A, B, C, D values, for a transformation from one relativistic inertial reference frame to another inertial reference frame. And we start with just our simple, got two reference frames. Here's an event. And that event has coordinates. Now, this here I took the picture from somebody else. And they have x, y, z, and t rather than ct, x, y, and z. But it has a different set of x, y, and z in one reference frame, a different time in that one than in the other. And so what we want to do is relate. Now, one of the first things we do is we simplify life by saying, let's work one-dimensional. That is, in space, we're going to have the velocity is parallel to the x-axis. We do that just so we don't have to worry about the three-dimensional velocity. We just assign the x direction as the direction of the relative velocities of the two reference frames. So technically, v here is equal to the speed of the s prime reference frame with respect to the s reference frame. Right? So the speed that this reference frame with the prime is moving with respect to the s reference frame, and it's in the z direction or in the x direction to make our lives easy. Now, if I want to find the x coordinates, I can say, well, if this guy here is going to measure the x coordinate, he of course can just measure directly x, or he could say it's the distance the origin of one reference frame has moved, v multiplied by time, because the reference frame is moving at the speed of v, plus what the person in the other reference frame is going to measure, x prime. And so he says that the distance is equal to vt plus x prime over gamma. Why over gamma? Different reference frame, the rule of the other guy measures is shortened to him, so that you've got to take into account the length of contraction. So taking that equation, just solving now for x prime, that means subtract vt from both sides and then multiply by gamma. We have x prime is equal to gamma times x minus vt. There's one of our two equations. Right? And come up here and say, aha. I've got to look at it again. X prime or gamma v plus minus v gamma. Well, yeah. And so I can read off of this, C must equal gamma v, and D must equal minus, wait, I did not copy something right. It was, oh, it's just gamma for the X one. Let me just zoom out so I don't screw it up. It's positive for the X and it's minus gamma V for the T. There's my sign. So that means C is minus gamma V and D is gamma. So I have two of my coefficients already. That was quick, which is good. Now I'm going to say, what works in one reference frame should basically work in the other reference frame. What's the difference in the reference frames? Well, basically, you see the other reference frames move in the opposite direction. So if you look at these two equations, the one at the top of the screen and the one at the bottom of the screen, this one here and this one here, is doing the same method but shifting your reference frame. And so now you have x prime is equal to minus vt prime, minus because in the prime reference frame you see the unprime move in the opposite direction, and then plus x over gamma because you're going to see their length contracted. Now if you take this and solve it for t prime, you find that minus vt prime is equal to, actually, no, I don't want to. I want to leave it just as it is. So now I'm just going to set the two x primes equal to each other. So set this x prime equal to that one. So I have gamma times x minus vt, that's the first one we found, is equal to minus vt prime plus x over gamma, and then solve that for the only prime variable, for t prime. So I went through the math here. One of the things that is a little surprising here to the people is that when I do this solution, I had gamma, I had 1 over gamma minus gamma. I factored out of gamma to get 1 over gamma squared minus 1, but 1 over gamma squared minus 1 is equal to that's brutal. Doing it the simple way, 1 over, bring it back on top. Square that, and it's 1 minus v squared over c squared minus 1. It's just minus v squared over c squared. So this thing here is just, and then since there's an over v here, that's why it's just v over c squared, not v squared over c squared there. And this v then also yes, it wasn't there. So yeah. And so we get this equation right here. So that now gives us two equations. This one we'd already looked at. Here's the new one. And so reading off our terms, the coefficient of time here was 1. The coefficient of x was minus v over c squared. And then the one we've already looked at, the coefficient for t was minus v. Coefficient for x was 1. So we now have the linear transformation between the primed and unprimed reference frames. This is, of course, only showing one dimension of space. The lengths in the y and z directions, the directions perpendicular to motion, are not contracted. And so we actually can make this a four-dimensional There's the equations in all four dimensions in linear algebra. You can see that it's quicker to write the equations like that than it is to write them like this. But this is the same set of equations that was represented by that matrix multiplication. And all of the work we've been doing was finding what you're going to have for time and position in the prime reference frame relative to the unprime. What makes prime and unprime special? The unprime is the one you're in. So what's the difference between the two reference frames? The speed of one reference frame with respect to the other is opposite direction. The sign of the speed between the reference frames is the only difference. So I can convert from the simply by changing the sign of the speed and changing from prime to unprime and vice versa. Notice here I've used the definition that beta is v over c because that also shortens things. Now we're going to look in the next 8 minutes at addition of velocities. So I was supposed to cover addition of velocities on Friday. I didn't get to it. That's what we'll talk about first thing in class tomorrow. Addition of velocities. First we define u is what I'm going to use for the speed of a particle. So I'm in my reference frame. I have this stopper. I throw it. The stopper has a speed ux in the x direction, uy in the y direction, uz in the z direction. So that's why I'm using u for the speed of my particle. V I'm using for the speed of the reference frame with respect to the other reference frame. So with those definitions, then ux is dx dt, uy is dy dt, uz is dz dt. That is so basic. And if I go into the prime frame, of course, ux prime is x prime, or derivative of x prime with respect to t prime, and so on. Then I have these Lorentz transformations. I want to go from this to being able to find the speed of my particle in one reference frame from another. Well, what I'm going to do, just wanted to make sure I didn't have them written there, is say ux prime is equal to dux prime dt prime. That was already written. It's equal to dux prime dt dt prime dt. Technically, what have I just done? Well, I what? Okay, I added an intermediate. What this really is the chain rule. I can use that's the explicit chain rule. I have, say, ux prime in terms of time, and I want in terms of time prime, I just do derivative with respect to time, and then do derivative of time with respect to time prime. So what I have is the chain rule, basically. So let's come back here, and let's do what is dx prime dt. Now notice these are exacts. They're not partials. So that's going to be gamma as a constant because that depends on the speed of the reference frames. We assume constant speed between the reference frames because inertial reference frames. But I'm going to have dx dt here, whatever that is, minus v. Well, what's the derivative of time with respect to time? 1, right? So there's dx prime dt. Notice I replaced dx dt with ux. And likewise, let's do dt prime dt. dt dt is 1. And dx dt is ux. So there's the bottom part, there's the top part. So I'm going to have ux prime is equal to of course the gammas will cancel. So there's the equation for transforming the speed measured in one reference frame to the speed measured in another reference frame for an object moving parallel to the direction that the two reference frames are traveling with respect to each other. There's also a perpendicular velocity addition I need to do. But that's my first one. Now let's compare that to what we have done in the past, Galilean transformation. Remember, the Galilean transformation was velocity of object A with respect to reference frame S, well, let's do S prime, is equal to velocity of reference frame A with respect to S plus velocity of reference frame S with respect to S prime. That was the way we did the Galilean transformation. Now, if we look at this, Ux is equal to the velocity of A with respect to reference frame S. Ux prime is equal to velocity of A with respect to reference frame S prime. And V is the speed of reference frame S prime with respect to S. So using those, I can plug them in to this equation, and I have Ux prime is V A S prime is equal to Ux is VAS minus VS prime S well, I put them in opposite order, it's correct, but I'm going to change it just because they're opposite order. The UX was AS. Now, if you look, there are two things different. The S prime and S are in opposite order. So let's shift that. The only difference in the speed of one reference frame to the other, with respect to the other, is they're measuring in opposite directions, so I'm changing the sign. So if I change the sign, it will change the order as well, or change the order, it will change the sign. Now, if you look at this equation, you compare it to the Galilean transformation. The top is the same. It's just we have the new denominator. And so the Galilean idea works great as long as the speed of one reference frame with respect to the other is small enough that this whole term is approximately zero. But if the speed difference is not approximately zero, then we're going to have a different answer. For the last trick, and the last trick is a quick trick, what about finding this value? Well, all I have to do there is dy prime dt is equal to dy dt, because y prime equals y, right there. And so that means that uy prime is equal to uy over the same denominator and so there's the transformation of velocity in a direction perpendicular to the direction that the reference frame is moving. Even though the length in that direction doesn't change, the speed does. Why? Because of time dilation, because time is traveling a different rate. So the length is the same, but it's a different time for the change of the length. So that is our derivation for the addition of velocities. And you can change from one reference frame to the other simply by changing the sign of the velocity for the reference frames. I'm out of time. I'm out of